average atomic masses and how you calculate them. So when you look at the periodic table, the numbers underneath each element symbol, that is an average atomic mass, or the atomic mass. It is a weighted average of all the stable isotopes for that particular element. For example, carbon has 2 stable isotopes, carbon-13 and carbon-12. You may ask, what about carbon-14? Carbon-14 is an isotope of carbon, but it's radioactive. Therefore, it's not stable. It doesn't exist long enough for this type of calculation. So for carbon, it only has 2 stable isotopes, 12 and 13. So you will not encounter a carbon 12.011 isotope. You will encounter a carbon 12, most likely, it's 98.9% abundant, or a carbon 13 isotope, less likely, only 1.1% abundant. Those are the 2 stable isotopes of carbon. Okay. 12.011, that is the weighted average of these 2. Okay. Just to show where that number comes from in a calculation, you need the following formula. The atomic mass is equal to the sum of the mass of the individual isotope in AMUs give myself a little bit more room times the abundance. As a decimal. So you might see this formula and you might encounter it in different ways. There are a couple ways to interpret it, but for our purposes, use this formula. Okay, the abundance as a decimal place. So each isotope, if we're talking about carbon here, carbon-12 and carbon-13 each get a term. So to use this in a calculation, we start with carbon-12. Its mass, it's been measured, as 12 with 5 trailing zeros, AMU. That's going to be multiplied by its abundance, converted into a decimal. 98.9%. Converted to a decimal, you divide by 100. Move the decimal over a couple spots. 0.9890. That's the carbon-12 term. The next term is for carbon-13. Its isotopic mass has been measured to be 13.00335 AMU, atomic mass unit. Convert its percentage into a decimal. Oops. So divide by 100, 1, 2, so 0.0110. And we have 2 terms because there are 2 stable isotopes for carbon. Boron has 2, for example, has 2 stable isotopes. You would have 2 terms for it as well. So you have a term per stable isotope. If you do that math, you get 12.01103, writing more decimal places than is necessary. But if you refer to the periodic table, the value for carbon's average atomic mass is 12.011. And that's what's calculated. The atomic mass is the weighted average of all the stable isotopes for that element. Doing calculations with average atomic masses. So here's an example of an isotope or an element with more than 2 stable isotopes in silicon. It's here in the periodic table. You're always able to find the average atomic mass in problems like this from referring to the periodic table. But silicon has 3 naturally occurring isotopes, silicon 28, 29, and 30. The mass and natural abundance of silicon 28 are 27.9769 AMUs and 92.2% respectively. The mass and natural abundance of silicon 29 are 28.9765 and 4.67% respectively. Find the mass and natural abundance of silicon 30. Okay. This type of problem, if you take all of the language, usually if you make it into a table, that will make solving this type of problem a little easier to view. So we have silicon 28. We know its mass in AMUs. And we know its abundance, that percentage. We can go ahead and convert that to a decimal. And you divide by 100, move the decimal to the left twice. Silicon 29, it's a weight of 28.9765 AMUs. And if we convert its percentage to a decimal, we get it 0.0467. The question's asking us about silicon 30. We don't know its mass. But we do know, at least implicitly, what its percentage is. Remember, all percentages must add up to 100%, or their decimals must add up to 1 by definition. The old saying, give it 110%, it's a nice sentiment, but for actual mathematical value, it's not true. You can't give more than 100%. So we can calculate what the percentage, or the percentage of silicon 30. So 1 minus 0.922 minus 0.0467 will give us the percentage of silicon 30. And I get that value to be 0.0313. That is the abundance of silicon 30. So what you would expect for the average atomic mass, it's most of the silicon in the universe is silicon 28, 92%, 92.2%. The average atomic mass, you expect it to be close to 28. When you look at it, it is 28.085. Now we go about solving the problem. Pause to write the formula. You have to know this formula in order to do these types of calculations. So each isotope, we have 3 isotopes. We will need 3 terms in the summation. Okay. So we start with silicon 28. Get everything into frame. Silicon 29. And silicon 30 we don't know, so I'm going to use the variable x times 0.0313. And all of that is equal to the average atomic mass of silicon, which again is 28.085 AMU. So now we've got to pause and do a little math. There's the intermediate math. So this term, everything corresponds. The combined terms, so subtract both the combined terms, so we get 0.9371 AMU is equal to 0.0313x. Divide both sides by we can solve for x. We get a value of 29.9392. Write more spaces than necessary. AMU. Just to be consistent with the masses that were given in the question, we'll include 4 decimal places, and that would round to 29.9393 AMUs.